So thank you for the introduction and welcome everybody to my presentation. First of all, I want to say thank you to Professor Vellekoop for giving me the possibility to stay on his institute for 3 months and work on the NCABRA project. And I also want to say thank you to Mahmuda, who helped me a lot with the fabrication of the devices. First of all, a short overview of my presentation. I will talk about the state of the art and the problems of droplet creation in microfluidic devices. Then about the idea and the device itself. Then we have a look on the single design elements to improve the droplet creation stability. Then we see a short simulation, the fabrication process and measurements, and at the end a short outlook and the conclusion. So many droplet-based microfluidic systems allow continuous single-cell analysis by including one single cell into one droplet. And they are creating the droplet by using a very simple structure, the so-called Tjunction. This structure we have here a main channel, which is normally filled with an oily phase, and we have a side channel filled with a aqueous phase. And the droplets are created, or the droplet size is strongly dependent on the inflow flow velocity. But if you want to have these cells included to the droplets and you want to use those as single micro-bio-reactors, then it's very important to know the exact size of the droplets, and so it would be much better to have a geometrically defined droplet size and not a droplet size dependent on the inflow velocities. So the first idea was then to fabricate different geometrical structures directly into the microfluidic channels to influence the behavior of the fluids. Here, for example, we see a PhaseGuide structure which helps to control the filling process of a reservoir. And we wanted to use this technology to stabilize the droplet creation. This is the device which we developed then. We have a channel height of 50 micrometers and a channel width of 100 micrometers. And we implemented then 3 different geometrical structures. Here you see the whole device. We have 2 inlets and an outlet, and we have a meander structure to see a bigger part of the channel. Then we have 2 pressure reservoirs, and here we see the 2 phase guides. One is directly at the position of the T-junction. The second one is a bit further in the main channel. And we have 2 boundary geometries named by M1 and M2. So if we now make a very simple experiment, if we want to slide a droplet over a phase guide with a constant speed, then you see that the pressure at the inlet increases because it's necessary to have an extra amount of pressure to push the droplet over the phase guide. If more than the half of the droplet is past the phase guide, we have a negative pressure, and then again a positive pressure when the droplet detaches from the phase guide. The amount of pressure necessary is, of course, dependent on the height of the phase guide, but also on the form of the phase guide. For example, if it's shaped as the droplet itself, then you need a higher pressure than if you have a straight phase guide. The second element we implemented is the so-called pressure reservoir. It's only an air bubble included into the system. And if we repeat the experiment from before and we apply such a pressure reservoir near the inlet, then and the droplet hits the phase guide, then you see that the pressure is very linearly increasing until a certain amount of pressure, and then the droplet is pressed over this phase guide, and the liquid stored in the pressure reservoir is flowing out again, and therefore you have a peak in the flow rate. That means that we have now an oscillation between the pressure and the flow rate in this device. The third element is the boundary geometry. It's the simplest element. We prevented the oily phase to flow into the side channel by applying a larger area in this region here. And we also applied a triangular structure in the main channel so that the droplet can attach faster to the lower boundary. Here we see the results of our console simulation. First of all, here we have the first inlet. This is the inlet of the oily phase. Then this part is the first pressure chamber. I filled this with the oily phase because then you can see very clearly how the aqueous phase is flowing into this pressure chamber. And I simulated this, or the behavior of the pressure chamber, by applying an inlet here where the pressure inlet, where the pressure is dependent on the amount of fluid which flowed into this channel. If we start then from the position A, we see that the upper part is filled with the aqueous phase. Then the pressure increases, the fluid is flowing into the pressure chamber, and if a certain amount of pressure is reached, then the droplet is pressed over the first phase guide, which is placed here, and flows into the main channel, attaches directly at the lower boundary, and blocks the oily phase to flow by it. We see that the amount of liquid which was in the pressure chamber flows out again and into the region between the first and the second phase guide. So, and in the meantime, because the oily phase cannot pass the droplet anymore, it has to flow into the second pressure chamber. Then the pressure increases. We see here the droplet is cut exactly at the edge of the Tjunction, and the aqueous phase continues again to fill up the pressure chamber. And if the pressure is large enough to press the droplet over the second phase guide, the whole procedure starts from the beginning. Here we have a short video of the simulation result. So you see that first the droplet flows into the pressure chamber till the pressure is high enough to push the droplet over this phase guide. Then the droplet flows into the region between the second phase guide and the first one. In the meantime, the oil is flowing into the second chamber, and if the pressure is then high enough to push the droplet over the second phase guide, the procedure starts from the beginning. So here we see the fabrication process. We designed this process like this, that we could do all the lithography steps at the beginning and then the etching steps. So I don't want to go deeper into this because I'm not an expert of these clean room technologies. Here you see the device which we came up. You see the channel structures. You see the connections for the pressure reservoirs. Here you see the phase guides and the boundary structures. The only thing I have to mention is that we had some problems because we wanted, so the initial plan was to manufacture everything in PDMS and cover it then with a parylene so that the material is not air permeable anymore. But as always with this clean room processes, the machine you need the most is not working at the moment. So the parylene coating was not possible. But nevertheless, we did some measurements. Here you see that means that if the material is air permeable, it means that the pressure reservoir worked only for a very short time because then the air vanished out of the pressure reservoir. But nevertheless, the rest worked quite well. We see here a droplet creation process. You see that the influence of the phase guides very well. The first phase guide here, the second here. And you see that the boundary structure prevents the oily phase from flowing into the side channel. Here you see that the droplet, due to the missing pressure chamber, is pushed over the PhaseGuide before the cutoff of the droplet. And here you see again how the aqueous phase is kept back by the first PhaseGuide. Then at the end, a short outlook. We have to do some measurements of the different droplet sizes. Of course, we want to use the fully working device, so we have to wait for 1-2 more months till the machine is working again and we can fabricate the first real working prototype. Then we want, of course, to compare the results of the simulation with the results of the measurements, and we want to vary the inflow velocities and see if it's possible to keep the droplet size constant also for different inflow flow velocities. And then we will improve the material combination. So in a short summary, so we showed some geometrical structures which improve the droplet size creation stability. We did a COMSOL simulation with this. And we showed a first not fully working prototype, but I hope that in the next months we can fix this and everything will work fine. So thank you for your attention.